Hello everyone. In today's video, we'll be talking about how to use the ICE system to solve for the concentration or pressure of compounds once they have reached equilibrium in a reaction. So far, this has been relatively unknown to us because we haven't been able to solve for these kind of problems. The numbers have always been given to us so far. And so in the previous video, we talked a lot about equilibrium expressions and equilibrium constants and how to solve and set up those things. In this video, we'll be talking about how to use ICE. Now, I will note that this video will not talk about how to use quadratics to use in the ICE system. There will be a separate video for using quadratic setup for ICE. This video will give you at least one number to use in order to solve for x relatively simply in the course of the ICE problem. This is to just sort of get you into the habit of using ICE and to show you how it works in the grand scheme of things. So ICE, of course, is an acronym, and the I stands for initial. So the initial refers to the initial concentrations or pressures of the reactants in the problem. Change is what C stands for, and this refers to how the compounds change over the course of the reaction. Reactants will decrease and products will increase over the course of the reaction, and we'll use the change in terms of x, either adding x or subtracting some x. And then E stands for equilibrium. So this is going to be the concentration of each product or each compound once the reaction has achieved equilibrium. So this is where we're going to take the initial and mathematically show the change that happens over the course of the reaction, and the equilibrium is going to be where we show the results of that change based on the initial. Okay, so we'll jump right into an example problem for ICE. So we're going to take the reaction chlorine trifluoride gas plus fluorine gas, F2, at equilibrium with chlorine tetrafluoride gas. And so let's say that 1.35 atmospheres of the chlorine trifluoride is reacted with 0.9 atmospheres of F2, fluorine gas. And so the question is going to be, what is the concentration of each of the compounds at equilibrium? And if what is the concentration of each compound at equilibrium if the final, if the pressure of ClF3 is recorded at 0.71 atmospheres at equilibrium. So this is might look a little rough in the writing sense, but the question is, if 1.35 atmospheres of chlorine trifluoride is reacted with 0.9 atmospheres of fluorine, what is the concentration, or what is the pressure of each of the compounds at equilibrium if the pressure of chlorine trifluoride is measured at 0.71 atmospheres at equilibrium? So because we're given this amount here as the equilibrium as the value of ClF3 at equilibrium, it eliminates the need to use quadratics to solve this. We can solve this because we have a final amount to set something equal to in order to solve for x. So what I'm going to do is I'm going to rewrite the equation down here so we can get to work using ice on it. So ClF3 plus F2 gives us ClF5. And so we'll set up the ice over here. So of course we know that I stands for initial. So this is going to be representing the amounts that we start with in the reaction. And so looking back up here, it says we start with 1.35 atmospheres of chlorine trifluoride, and we start with 0.9 atmospheres of F2, fluorine. Now, since chlorine tetrafluoride, ClF5, is our product, we initially start with 0 because it's our product. We haven't made it yet. Now C is going to represent our change. And we're going to write this in terms of x. And so I'll write out the change and then I'll explain what it means. So basically, we write the change in terms of x because that's the amount by which the reactants are going to decrease, and it's the amount at which the products are going to be created. They're going to increase. And it's some unknown term at this point. We don't know at what rate yet that the products are created and that the reactants are depleted at. We don't know that yet. That's what we have to solve for. And so the number that's going to come in front of this x term is going to come from the coefficients in front of the compounds. So each of these compounds has a hidden 1 in front of it. We just don't write it because it's 1. But since each of these compounds has a 1 in front of it, there's a 1 in front of each x. That changes depending on the coefficients. For example, let's say hypothetically we had a 2 here. We don't, but let's say hypothetically we do. then we would have a 2 here. But since it's a 1, we keep it as -1. The reason that these have negative signs in front of them, -x and -x, is because these are reactants. And over the course of the reaction, they're depleting. They are going down, and so we represent that with minus. Our reactants are decreasing throughout the reaction. The same logic goes for the plus x for the product. The product is being created over the course of the reaction, so we represent it with a plus x. And so for our E, for our equilibrium, we're going to represent this as the final state. So this is after the change has taken place. And this is ultimately what we wish to solve for. And so we know that for our product, it's literally going to be just x. For ClF3, it's 1.35, what we start with, minus the x, what we change. F2 is going to be 0.9, what it started with, minus x, which is the change. However, the question gives us the amount of ClF3 that exists at equilibrium. So we know that this amount is going to equal 0.71 atmospheres, because that's what we measured in the question. That's what we measured the partial pressure of ClF3 to be at equilibrium. So what we can do is we can set this 1.35 minus x equal to the 0.71, which will allow us to solve for x, which will allow us to solve for these other two compounds, what their pressures are at equilibrium. So what I'm going to do is I'm going to set 0.71 equal to 1.35 minus x. And so what you want to do is subtract the 1.35 to the other side, and then divide by -1 to solve for x. Just very simple algebra, not complicated at all. And so when you do this, you should end up with x equaling 0.64. So your x should equal 0.64. So if you wanted to keep sort of a running tally of the concentrations, or in this case the pressures, at equilibrium for each compound, for ClF3, our pressure at equilibrium was technically given to us in the problem. For F2, we're going to solve for it by subtracting 0.9. So we're going to subtract from 0.9 the x. So we're going to plug in what we solved for x into this x. So we're going to subtract this by 0.64. And you'll end up with 0.26. atmospheres for F2. So this will be your answer for F2. This will be your answer for ClF3, and then for ClF5, it's literally just X. So we just plug in what we solved for X, which is 0.64 atmospheres. So these numbers here in boxes are the pressures of these compounds once equilibrium has been achieved. So if you had a final step, which is to solve for Kp, we'll set up one of our equilibrium expressions, like we did in the previous video, where we'll have 0.64 divided by 0.71 times 0.26. Do that math really quick, which I will do. And you should end up with a Kp of 3.47. So this is our equilibrium constant for this reaction. And that's about all that we're going to do for this video. In the next video, we'll talk about using ice. Using ice with the quadratic setup, where we don't have one of our final amounts solved for already, and we'll have to figure it out ourselves. Until then, this is all.